Forward TV. The world is thinking.
Welcome to Fusion and the Future of Energy. My name's Rob Clowes. I'm from the Brighton Salon. We're just having a couple of little AV problems, as is often the case with computers. I'm just going to introduce the cast this evening before we get going. Before I started, I just thought I might mention one little thing by way of introduction. It's a quote from a presidential hopeful, one Barack Obama, and it just, I think, illustrates something about, from last year, something about the sort of politicisation of energy at the moment, and the importance of energy in many political discussions. Here's Barack Obama. He says, "The tyranny of oil funds everything from the madrasas that plant the seeds of terror in young minds to the Sunni insurgents that attack our troops in Iraq. It corrupts budding democracies and gives dictators from Venezuela to Iran the power to freely defy and threaten the international community. It even presents a target for Osama bin Laden." So I think that's kind of quite interesting, and I think we all know that the question of oil at the moment is one which is sort of uppermost in our minds in many discussions. What's interesting about what we're going to talk about tonight's fusion is that it's a radical technology that threatens. Is that it's a radical technology which sort of threatens to or promises to open up a whole bunch of questions and arguments which we've perhaps been taking for granted. So we're very lucky this evening. So for the first 15 minutes, 10 or 15 minutes, Professor Bob Bingham, who's on my far left, who is Professor of Physics and Laboratory Fellow at the Rutherford Appleton Laboratory and Strathclyde University, and is a leading light in a hyper project, which you're surely going to hear more about. He's going to introduce fusion, at least one project in its current state of the art. So we'll hopefully go into that very shortly. Then I'm going to, after that 15-minute introduction, what I'm going to do is I'm going to give very brief comments to other members of the panel in the first instance. They're just going to kind of bring up a few points for us to consider. I'll introduce them to you now. On my far right is Michael Massey, who is Associate Fellow in Energy, and Associate Fellow in the Energy, the Environment and Development Programme at Chatham House, and has worked for the DTI in a whole series of projects, including coal privatisation and a number of other possibly less controversial projects. On my near right is Dr. Alex Penn, and she works at the Life Science Interface and is actually Life Science Interface Research Fellow in the Science and Engineering of Natural Systems Group at the University of Southampton. She's also has a fellowship at the Collegiate Budapest Institute of Advanced Studies, and her sort of background is in physics and more recently in complex systems science. And on my immediate left is Joe Kopinski, who's a science writer based in London. He's a frequent contributor to online magazine Spite. He's got a forthcoming co-written book out called Energize, which I've had a chance to have a look at some of the early versions and threatens to be incredibly interesting and shake up the debate a little bit. So, without further ado, ready to go?
Yes.
Give you Professor Bob.
Well, thank you very much, Rob. I'm delighted to be here, actually, and I'd like to thank Rob for inviting me to this new venue. We've been here, we haven't been here before, actually, but it's going to be a privilege to talk you through some of the things that we're doing in the laboratory. I'm representing HYPER, which is a pan-European project for energy and science, and this project is all about energy from fusion. We're trying to actually extract the energy that is the energy in the stars. And this is the energy that is natural energy source for the planets that exist round about the stars. So the idea is, could we build a miniature sun on Earth, and could we use it to power our civilization? The idea that we're going to be talking you through now is one that has only recently been realised in the last, say, few years, actually. Before I go on to the HYPER story, I'm going to talk about a couple of issues that are really dear to our hearts at the moment. That's energy. Energy is a major problem in the world at the moment. We've seen oil prices fluctuate violently. And as far back as the 19th century, Ludwig Boltzmann coined the phrase, the struggle for existence is a struggle for available energy. And on this graph, what you see here is the energy usage in the EU. I'm going to be talking about the EU, not the world's energy usage, but the EU is increasing 2% per year every year. And this is up to 2006. We've got the latest figures for 2006. We haven't got them for 2007 yet. And what you find is that at the moment we're using a lot of our natural resources. If you look at this graph here, yellow is for the oil going round clockwise, then it's blue for gas, then coal, then nuclear. And you can see that the hatched area, which is a very thin part of the pie chart, is the renewables. Somehow or other we've got to be able to increase that as well as decrease the others, and perhaps fusion will help us to do that. I'll come back to this at the end of my talk. If you look and see the oil reserves that we've got, the gas and coal as well, they're not very long. I mean, we'll get 36 years up to 196 years. That is not a great deal of time to actually sort out our future energy needs. The share of reserves in the EU is pitiful. We've got 0.5% of the oil in the world, which is not very much. We get 1.3% of the gas and about 3.9% of the coal. The production and consumption, again, is not very good. We're using up more than we actually produce, so we have to import most of our energy. This is where we turn to another fuel. It's called fusion. And this is a very elegant way of solving one of the problems. It's the natural fusion for the stars that have been shining for millions of years. And what basically happens is that two isotopes of hydrogen, a deuterium isotope and a tritium isotope, are fused together to form helium and a neutron. The helium heats up the rest of the fuel. It's sacrificed to heat the fuel, but the energy is carried away by the neutron. 14.1% 40.1 MeV of the energy is carried away by the neutron. This is an example of how much energy we've got in a cubic kilometre of water. The cubic kilometre of water contains enough deuterium that is in the world's oil reserves. So we've in 1 cubic kilometre, and remember that deuterium is 1 part in 6,000 in water. So 1 part of the water, which is H2O basically, 1 part of the H2O is D2O, and the deuterium is 1/6000th of that. And this is an example. This bottle of water and a rock, which is containing lithium, which we haven't discussed but we might go into later, actually contain enough energy to fuel a family of 4 for about 1 year. So far, I've just talked about the ideas. Now, at the moment, we're entering a new realm of fusion energy research. On the right-hand side is a description of ITER. ITER is the energy production or the energy research process that we've been using for the last 50 years. That's a magnetic bottle. You're containing the plasma, which is the ionized form that we like to call a plasma. We're containing that in a magnetic bottle. In the left-hand side is a picture of NIF, which is coming to completion. They're actually running it at the moment. And they're going to be demonstrating laser fusion within about 3 to 5 years. The commitment of fusion through ITER, NIF, and the LMJ. ITER is the fusion reactor that's being built in southern France. NIF is the American one, which is the National Ignition Facility, and LMJ is the French one. We don't have one at the moment, except we've got HYPER. HYPER started up operations just a few weeks ago. The launch was held here in London a few weeks ago, and so we're moving towards tooling up and building an exciting new way forward for the energy of the future. So putting numbers into perspective, actually, the idea of HYPER is going to use lasers. Lasers have been around since about 1960. Some of them are very powerful. We've got one of the most powerful ones in the world at the Rutherford Appleton Laboratory. So the energy is about 500 joules in the one we've got. Now a Kit Kat is about a megajoule. So it's much more energy in a Kit Kat than there is actually in the laser photons. However, the timescale that this energy is released in is extremely small. It's 40 femtoseconds. When you combine that together, it gives a powerful laser beam. And this power is equivalent to 1 petawatt, which is 10,000 times the national grid power. That is released in a fraction of a second, 40 femtoseconds. Now, if you focus that power onto a spot smaller than the width of a human hair, you would get equivalent to 10 to the 9 atmospheric pressures. So that would be 10 to the 9 gigabars of pressure. That's equivalent to stacking about 10 warships on your thumb. So how do we do this? We do it through a process of fast ignition. And this is to use very powerful multi-petawatt lasers. The idea is you take a pellet which is containing deuterium and tritium, you focus your lasers onto that pellet, you compress it to about 300 grams per cubic centimetre. A teaspoon of this material would weigh about 300 grams. That is quite a high compression ratio. As you're getting close to the maximum compression, you ignite the fuel with a second laser, a much more powerful laser, and this sparks off the reaction, the thermonuclear reaction. This concept is about 10 times down in cost for conventional fusion processes. It also breaks the link with defense science, we can go into that later. It allows a civilian approach to be used, so we don't need to involve any military secrets at all. This is an idea of what's happening. This is the animation of the pellet. We're looking at half the pellet. We've actually fired the first laser. This will run again. Fire the first laser, there it goes. You're ablating material. The material that's moving off rapidly is actually being used to compress the fuel. When the fuel is at maximum compression, i.e. maximum density, you fire the second laser, which then ignites the fuel, takes the fuel up to the temperature that is required for thermonuclear fusion, which is of the order of about 40 keV. This process would then release about 10 megajoules of energy each pulse, and you do this, say, 10 times a second. Inside the chamber, you've got an enormous amount of energy waiting to be released. This is an example of just what we're talking about. A 100-ton coal hopper runs a power station of about 1 gigawatt power station, which is a typical size of a power station, for about 10 minutes. The same hopper, filled with the fuel that we use in these ICF targets, would run the same power plant for about 7 years. That would be consumed totally. There would be no radioactive waste from this material. The only radioactivity you would produce would be the walls of the chamber. You would have energy security. It's clean, there's no carbon emissions. It's safe, there's no stored energy, so you wouldn't be storing up huge amounts of radioactive or any other kind of energy. Complementary solutions exist. The laser is a pulse solution, so it can be switched off and on relatively easily, whereas the magnetic device, you want to have it switched on and you want to keep it running for a while. And the fuel that you're going to be used is the hydrogen. This is an example of the ignition scheme that that's underway. I won't discuss this since it's quite technically difficult. But this is what exists already. It's a 10-meter diameter chamber. You see right in the center of this chamber is a climber. He's actually looking at one of the windows through which one of the lasers will be passing. We're using many lasers to actually ignite the fuel. It's the center of the pellet. But they're all coming from the one basic source where we split it up by mirrors. You could say it's all done by mirrors. The implosion laser that we're using is about 200 kilojoules. The present lasers that are being built and are built at the moment is 1 megajoule. So this is an order of, almost an order of magnitude less energy than the ones that are being built at the moment. It's a spark plug system. What happens is that the second laser that we have ignites the fuel, and we'll show that in a second. This is just an example of the target chamber. This is the one that's existing already in Livermore, that's being completed. I showed you that picture right at the beginning. So the idea of inertial laser fusion is very similar to the internal combustion engine. What we have here is you have a driver, which is the laser beam. You have a target factory, which is the top of the picture there. That actually creates the little pellets that contain the isotopes of hydrogen of hydrogen that are going to be dropped into the target. You ignite the target with the lasers. The energy is released in the form of neutrons. That's captured in the wall. So the laser fusion is almost analogous to the internal combustion engine. So there's a diesel and there's a petrol variant. Now, I said that I would go back to the argument about energy from the beginning. So this is an idea of how fusion will actually help to integrate into the renewable and the other processes that we have to actually invest in to reduce the CO2 emission. On the left-hand side, we've got the annual supply in terms of energy. So this is in terms of exajoules. And along the base here, we've got the CO2 concentration in terms of parts per million. The green is renewable, blue is hydro, yellow is fusion, red is fission, purple is gas, and black is coal. You can see what we're trying to do now. We're trying to wedge fusion into this energy supply system, make it grow, and it will be growing at the same time as the renewables. So we're actually taking a system of fusion and we're reducing the coal and the gas and the oil dependency. And we're making that a bigger fraction of our use. You've also seen at the end here, we've still got a small amount of nuclear because we do require nuclear energy to be running in the next few years. We still will have, say, coal-fired power stations because some of the poorer countries might not be able to afford this technology, so they'll still be running on coal and gas. But this is the idea that we've got in terms of bridging the problem with CO2 production and energy production. So in summary, we are entering a new era for fusion energy. We've already demonstrated that fusion actually can produce energy from the tokamaks. The idea that the laser in Livermore will be operating in the next 2 years and demonstrate gain, and that's the important thing. The tokamak has not shown gain yet. The one in Livermore will actually show gain. The development of lasers in the last few years has allowed this scenario to be developed. We're now working in a transnational capacity with all the European partners, and we're also discussing with America as well. The next stage, which is ongoing at the moment, is the detailed facility design. That's going on at the moment. We've got the money from the EU to put this forward, and the international connections are already in place to develop the next fusion process based on the hydrogen compression by lasers called HYPER. Thank you.
So I'm just going to invite the other respondents on the platform to raise a couple of questions. And very quickly, I'm going to throw it open to the audience. So, Michael Massey, I know you have some thoughts about where blue sky research and the possibility of fusion should fit into our sort of broader energy policy. So perhaps you might want to say something about that.
Just a few quick remarks. Yes, it does seem to me, I was slightly tangentially involved in funding of decision to fund HYPER when I was in DTR, and I also worked on sustainable development, so I did more than just close down coal mines. What is clear, I think, is that we have significant energy problems, even leaving aside climate change. Climate change makes it much more challenging. We need more energy. Fusion, I think, offers sufficient potential to make it worth investing public money in, and doing it on an international collaborative basis seems to me the right way forward. I don't think that necessarily doesn't exclude, it should not exclude doing other things in the meantime, for example, improving energy efficiency, and I would say another area where public funding is justified is in carbon capture and storage, because we will carry on using coal, and other countries will carry on using coal, that is for sure. So I think fusion does offer promise. The big question is, and it does justify putting money in, but the big question is how much money should we put in and for how long? So I was involved in some of the discussions about HYPER back in DTI days. People made the slightly smart-arsey comment that this is one of those technologies that is always 30 years away. Now that needs to be brought down. It needs to be show promise within a reasonable time scale. I'm not sure what that is, but it needs to show sufficient promise that it will become a commercial proposition, not a very interesting scientific experiment. So it does seem to me to fall into the sort of category of a project or research where I'm not sure how blue sky it really is. It seems to me it's sort of reasonably applied. It's perhaps a bit more applied in the blue sky. But it is something that's justified. But the big question always is, how much money should we put in, and how patient should we be continually putting public funds in before we're starting to see results. And this has to be seen against the background of experience on the nuclear fission industry, which was so oversold in its early days. It's energy so cheap you won't have to bother metering it. That has bred, leave aside all the safety issues, but that has bred an awful lot of cynicism, and I'm sure technically colleagues will explain why fusion is very different from fission and so on and so on. But nevertheless, there is that cynicism, and it needs to be overcome, so we need to be seeing the research actually producing promise fairly soon. But as a proposition, I think it's a very promising one, and an essential part of a scour of all the possible energy sources which we need to be looking at, both in terms of energy security, economic development and climate change.
Thanks very much. In 1975, Stanford University professor Paul Ehrlich wrote that giving the world cheap or just more energy would be like giving an idiot child a machine gun. It's not clear that well, at least in the debate, it's not clear that energy is just something which would solve all our problems. I wonder if, Alex, you'd like to sort of just reflect a little bit more on sort of the context in which we might use more energy and some of the other problems which this might not solve in a simple way.
Sure. So I think it's very important that we realise that we can't just pursue a business as usual approach with fusion. I think fusion is a fantastic and very exciting technology, but just simply replacing our energy supply, our fossil fuel energy supply, is not going to solve all our problems. I don't actually subscribe to this view that humanity would be like an idiot child with more energy, but I think we do actually need to reevaluate ourselves in the context of our existence and we're very powerful players in global energetic and metabolic cycles, not just of energy but of nitrogen, carbon, clearly, the material flows of the planet. And at the moment we have a very limited capacity to manage these kind of complex ecological evolving systems, of which we certainly are part and we influence to a large degree. So, the Millennium Ecosystem Assessment identified 24 ecosystem services that they could reliably talk about with good data, and 15 of those were said to be in decline with respect to their ability to support human populations. So I think we genuinely are going to come up against these problems also. And that's not to say that we can't deal with them, and energy will help us tremendously in dealing with them. But what we really need to do is think about these systems as complex systems. A lot of these ecological systems have the capacity they're nonlinear systems, they have the capacity for rapid collapse, for tipping points, as they're sort of colloquially known, to evolve and sort of change in ways that we don't predict. So classic examples of our bad management of such systems are antibiotic use causing MRSA, for example. We really, really need to take whole systems approaches, to take intelligent, complexity-driven approaches to how we interact with natural systems, and to transition to sensible management and interaction with those systems. And that doesn't mean going back to sackcloth and ashes, but we need a different approach to, and just more energy is not the only solution.
Thanks a lot, Alex. So, Joe, I know you're busy completing a book at the moment which tries to look at energy use and energy policy in a much broader sort of socio-political context as well. But perhaps you have a somewhat different perspective on it to Alex, so perhaps you give us some background on that.
I think that the way in which society is able to innovate in energy is fairly profoundly affected, especially right now when energy has become centre stage, by wider kind of political and cultural trends. So I think Barack Obama made a quite revealing remark in criticising Bush's response to 9/11. When Bush said, well, what I want you to do is all go out and carry on shopping. And Obama said, well, what he really should have done, what I would have done, is rally the country around energy independence. And I guess you could gloss that as, instead of go out and shop more, go out and shop less. Use less energy, use less resources. And I think that outlook, which brings together a sense of being under siege, whether it's from being held hostage overseas, and we saw some of that data perhaps in Bob's initial presentation, or under siege from the kind of fragmenting natural world and the falling apart of the ecosystem services, is something that quite profoundly informs the way in which energy decisions are made today. And I think you can see that even when there are attempts to put forward a quite ambitious program of energy innovation. So you can see people talk about a Manhattan Project in energy as what we really need, and Al Gore talking about how we need to decarbonize all our electricity in the next 10 years. Kind of sounds like an ambitious program, or Greenpeace, whose latest campaign for an energy revolution, as they call it, although they do hedge their bets with the R in brackets, perhaps just they're more evolutionary than revolutionary, but they very much invoke JFK and Kennedy and the Apollo moon program, and the idea that this is what real leadership is about. But I think when you scratch the surface of these ambitious-seeming programs, then they don't really get past this sense of being under siege. I think the idea of the Cold War with Kennedy, or the Second World War with the Manhattan Project, gives this sense of the crisis as the thing which is pushing us forward. The immediate danger to which we have to respond. And I think that kind of context makes it quite hard to rationally invest in a program like fusion, which is not going to pay off tomorrow perhaps, or even next year, right? But is something which, if we invest in the basic science and technology, is going to provide a basis for a long-term contribution. Well, not that there's any guarantees of these things, but has a very good chance of paying off in the long term. So we need to be able to step back and have an appropriate sense of ambition and long-term development in our investment in new energy technologies, not panic, think we've got to solve the whole problem tomorrow, but really start thinking big in a bit of a deeper sense.
Okay, thanks very much, Joe. Now, as you know by now, the lifeblood of the Battle of Ideas is audience points and questions. So we've got quite a long time for that. Or we've got a small amount of time, but we've got a long slice of this time for this. So if you could put your hands up, I think there's 2 microphones coming round. 1 microphone, 2 microphones. So if you put your hands up now, I can see who wants to speak. Points and questions, and I'll try and remember you. So there's one close to you there. And there's one down here. So you, sir, first.
Yeah, I'd like to thank you for a fantastic presentation, very interesting about nuclear fusion. And I think it's something which kind of excites us all to think about future energy supply. But I think it's important we put it in the kind of context of what is practical and political ambition. And also, I'd be interested in your comments about nuclear fission, because it seems that there's a lot of excitement about nuclear fission solving future energy problems due to the high level of discussion about climate change. But given the dearth of building of nuclear fission power plants over the last 20 years in the OECD, there seem to be real practical problems about expertise and the ability to develop nuclear fission. And given that gap, how politically practical is it to pursue nuclear fusion?
I could just give a quick answer to that. They actually had a machine called JET, and that produced 16 megawatts of power. Now that was limited because of the size. I could go into the details, etc., but it was really limited because of its size. The one they're duplicating, which is going to be bigger though, in Cararache, which is south of France, is going to be 500 megawatts, which was very close to a power reactor.
Just following on from that, actually, the project at Cullen, I've been to that several times, taking my kids there. I'm a physics teacher, so I got interested in. It's an amazing place, and the experiment there, you showcase we've got something hotter than the sun going on in Britain. Weird part of Oxfordshire. No one knows it's there. Even more interesting is next door. There's a British one, which is Heath Robinson. And they built their own one next door, and they fire pellets in with an air rifle just to see. So it's all this mad stuff. But then I went back about 2 or 3 years ago, and something had changed. No longer was it like a wacky experiment that someone had forgotten in the corner, which is literally what happened. But these guys were saying, well, at least we're not fishing. Dirty fishing. We're green, And the if you like, reigniting the argument around fusion has been done around the whole point that we can now sell ourselves as a green fuel source. And that's the reason why ITER suddenly got funding and suddenly got a base after however many years that they've stretched out Cullen. So, I mean, I would really like to hear your comments on that, because I think that we've got a real problem, because we can't justify fusion on the basis it's not fission, because we need fission now to fill the gap. We have to justify that and argue for that. So, am I right in saying that there's this kind of, at least we're not them attitude?
Okay, well, I'm going to take maybe two more points. You move the microphone up to there, and then I'll bring in the panel again.
I'm Joe's co-author on Energize, the book you must buy from Beautiful Books before Christmas, if we have it out by then. I had a friendly question to Alexandra, which is, you say, before turning to Bob, you say that so many of the processes in these magical, in my mind, mystical ecosystem services are non-linear, based on complexity, presumably a succession of tipping points, and therefore more energy doesn't really solve all of these problems. Do you see any connection with this sort of succession of tipping points when something bad goes to worse and then worse still? Do you see any connection between that and the ladder of escalation in the Cold War that was always talked about? How a trip here would lead to a fall there, and things would get worse and worse. And if you did see a connection, wouldn't that make you wonder whether the pellets and lasers that Bob had described, were they terribly complex and full of tipping points? And is that really how the world works? But turning to Bob, I was sad that the first bullet point, not too many bullet points, I'm delighted to see, or pellet points, but the first bullet point that you made for rationalising it wasn't in fact the green thing, although I very much agree with the remarks made before. But I thought it was also a defensive point of departure, namely that you can guarantee energy security. Don't you know that lots of Greens will say that deuterium supplies and lots of other things are limited, and the one source of energy that doesn't have any security or supply problems is wind power, or sun power, or hamster power, or dung power, and so on. I think it's a useless point of departure. It is in fact Obama's point of departure. Energy security. And once you've used the word security, who the hell is going to buy a fusion reactor?
Okay, so one more point just here. And if you could get the microphone to the back, it looks like there's a couple of points on there.
Now, I don't want to use the expression naive, but it seems to me that at least two of the panelists seem to be absolutely overcomplicated the problem by saying that we need to consider it in sort of wider either socio-political context or in the context of ecological systems. Because the problem fundamentally to me is very simple. There's 2 billion people being lifted out of poverty who will need to, or who will want to consume. And all we need to do is basically just find a way of producing energy cheaply which will not affect, or will affect the environment to least possible. And I think saying that we need to consider issues in broader context and all of this warfare doesn't change anything, because the truth is that there is no way that you can stop the 2 billion Chinese and Indians just consuming more. So the question is not what you would like to do, but what is actually possible. And in that context, the only option we have is actually to build more and secure that supply, because otherwise we're just going to run into huge issues very, very quickly. So I think discussion about whether it's right for us to want more or whether it's right for us to be very consumer-driven is a question or a discussion that we can have in sort of 100 or 200 years, when we know that we have enough energy to actually secure survival of us, and then we can debate whether it's the right sort of way to happiness. But in the short term, I think it's sort of the 10th or 100th priority in sort of order of things we need to look at. And if you could comment on that, then possibly, I think both of you. Thank you.
Okay, thanks very much. We can move the microphone to this guy here. I'm just going to, if you wouldn't mind just holding on, I'm going to bring in a couple of people from the panel. Michael, I just thought I'd invite you to say, as you were part of the government agency which funded, I don't know if it's a hyper project, but it was the ITER project. Yeah. Do you recognise this point which has been brought up by a couple of people that it's because fusion is not dirty bad fission that funding went into it, and if that's the case, you think that's very problematic given we still seem to need nuclear fission and we're going to need it in the short and almost certainly the medium term as well.
I'm not sure it was that significant, frankly. I mean, it would have been, put it the other way, if it wasn't distinguishable, its environmental consequences weren't distinguishable, then it would have been a no-hoper. But it wasn't funded because, brilliant, we've now got this magical green source of everlasting energy. It was seen as a project with enormous potential, and as a way of these things, building on a fair amount of UK expertise, which often is a reason for putting money into things, because we think this is good for the UK. So I'm not sure it was. It was less of a positive factor, I think, than may have been indicated. Because on the other question, the only other point I would make is related to the point about the fact of the matter is we will need enormous amounts of energy. That's why I am very disappointed that the UK government talks a lot about carbon capture and storage, but isn't prepared to actually get on and do something to bring it to make it a commercial proposition. Because the fact of the matter is, the likes of India and China will use enormous amounts of coal. They have no choice, and to deny them that is actually telling them they're not allowed to develop, which is completely wrong and outrageous and impractical.
Thanks very much, Alex. So, seeing as there is a question directed to you about tipping points. Perhaps you'd like to respond to that, but also perhaps you'd like to say something about if it is the case that which it seems to be the case, that much of the world really needs this energy. I mean, how much should we take account of the worries which are being put? How should we balance our worries about complex systems against the very real needs of people to industrialise and have better lives and all of those kind of things?
Okay, so firstly, I'm afraid I don't know much about the Soviet Union, so I can't answer that specifically. But I would say that in terms of cascades of tipping points, then we do have very good evidence that genuinely is how the world works. It's certainly how ecosystems work. There's a lot of evidence for biostability in ecosystems. So, the classic example is the Sahara switching from desert to forest. And there's a lot of evidence in those systems. It's not that things are sort of getting worse and worse. It's just that you move to a different regime, which is characteristically different. And then it's not easy to switch back again. You have hysteresis in the system. So even if you put the climate back to the same levels of precipitation and temperature, the system doesn't switch back in a linear way. It gets stuck in ultra-stable regimes. And that happens in economies, in terms of people keeping... That's what a poverty trap is. It happens in ecosystems. So these things do genuinely exist. There are a large number of complex, interacting, evolving systems in the world with which we have to deal. But I'm afraid I can't comment on the Soviet Union. So I'd say, yes, that definitely does exist. It is how the world works. We do have these tipping points. They do exist. But in terms of... I can't answer the question of precisely how we balance the need for development and energy in developing countries with the problems of ecosystem services. But these problems do exist, and they're urgent problems. So I don't think it's just a sort of naive response and it's something that we can leave till later. I mean, in China, desertification is a huge problem right now. In sub-Saharan Africa, food production is falling simply because of degradation in ecosystem services. These are real problems and they exist now, and we need new approaches to dealing with these problems because, of course, people need more energy, and I agree we should go for these technologies, but we need to use the energy in new ways. We need to develop the science, the technology, the innovation, the sort of the way of thinking about these systems, that we have to think on a whole systems level and about how systems interact, coupled social, ecological and economic systems, because we can't just carry on as business as usual. It won't work to just say, we'll just give these people energy and then we'll deal with these consequences later, because we do have genuine problems, and they're not insoluble problems, but they'll take innovation and a great deal of work to solve. We have to do it now.
Okay, thanks very much. Joe, I don't know if you wanted to come back on this question of complex systems and balancing it against the real need for energy in the developing world and here as well.
Yeah, I mean, I think that brings together a few things in the sense of anxiety about what's going to happen with all this energy. I mean, I think it's true that ecosystems are complicated things to try to understand and deal with. I think the best way of trying to get a handle on the complexity of those things is to manage them rather than to act as a spectator, ultimately. I think that, often the most scary scenarios are rather overdone. I mean, you may remember a few years ago there was much concern that the Gulf Stream would switch off. I mean, the film Day After Tomorrow was kind of a rather overhyped version of the story, but nonetheless there was a certain amount of serious scientific speculation or theorization on the point. It turns out, well, actually, perhaps historically it may be a possibility, but right now we haven't pushed the thing in a direction where that's on the agenda or likely to happen. So I think that many of these examples of tipping points and the rest of these things are overdone in the kind of panic mode. And just to kind of take the point a bit further in terms of practical consequences of worrying over these various accidental consequences, the tipping points, where I think there's a similar kind of anxiety around the proliferation of nuclear technology, whether it's kind of proliferation of nuclear weapons has this sense of kind of an out-of-control process of one thing leading to the next, a little like the idea of nuclear meltdown itself. I mean, the kind of image in the public mind of all these things is kind of runaway processes. I think does come together, and we need to understand that does have consequences. Someone says, well, actually, why does it matter to worry about the kind of cultural aspect and the cultural understanding of all these things? I think when you look at the impact that these fears have had on, as the first question that was raised, shutting down the research into fission, you look at the way in which, the government seems to talk, has been said about CCS, right, doesn't get done. Nuclear fission doesn't get done. People are able to talk endlessly about new plans for new forms of energy. Recently when the solar energy industry decided that they might get serious about covering the desert in the southwest in the US with concentrated solar power generation. The federal government decided, well, actually, hang on, there's a lot of wildlife in those deserts, and we actually have to put a moratorium on building solar power in the deserts until we've actually had a complete assessment of the impact that this is going to have on the lizards and snakes and the rest of it that live in the Arizona desert. And you can see that there's a very powerful consequence to the kind of cultural anxiety which attaches itself to any new innovation and development. And unless we actually tackle that head on and make the case for more energy, both in the developing world and also as it happens in the developed world, and even in the US, right, where they use more energy per head than anywhere else, they need a lot more energy too, right? Then it's not going to get built. So I think that's why it's important to raise these questions and make the case for more energy.
Okay, thanks very much. Unless you want to respond immediately, Bob, I might hold you back a little bit and try and bring in some more people. So there was a point. Somebody at the back has got a microphone, I think, already. If you could make your point or question, and put your hands up if you want to get in.
So anyway,
please.
Yeah. Okay. So I was wondering on the limits on such creation of energy. Like, I agree that nuclear energy is such an ambition, a big step forward, and then there's the setbacks of considering what would be the cost of supporting these infrastructures on like nuclear fission stations. And I was also wondering about, would it be cheaper to possess renewable energy rather than nuclear energy, which would be safer in the far, far future than having nuclear energy, which is to be hazardous and which might ruin the environment as well as the, what do you call it, the climate change.
Okay, thanks very much. Could you pass the mic on to the lady that's there just in front of you, actually? But there's somebody down here who's got another microphone. Yeah, you've already got one. Could you please?
It's partly been covered already, but I think it needs pushing.
And keep your hands up, sorry.
The idea of how complexity theory is used, because I think it is. I don't promise to be an expert on it or anything like that, but I think it is used as a default for cases which appear complicated. Now, just as an example, I think it's possible that a lot of things are actually linear with lots of noise on. A lot of people would assume they're complex because it's maybe difficult to get the underlying information out. And I just do think a lot of times it is lazy thinking that applies the complexity theory, complexity ideas. Even the idea that just because something's non-linear means it's unstable or potentially unstable is wrong. I think. So I just think people need to be more critical about just using complexity as a possible explanation of systems.
Thanks. If you could hand it to the chap in the brown jumper in front of you. And if it's who's got the other microphone? Yes, please.
I just wanted to ask a question, which is fusion and fission. When we talk about nuclear, I thought fusion was something that we were nowhere near ever coming toward having. But I also thought that fusion, if we did have it, was completely safe, that it produces no nuclear fallout. So is that true or is it not true? And also, if we start to use water, maybe it's a very small amount of water, but stretched out over, it does make you wonder, since we're short of water anyway to try and deal with all our problems, it does just make one question. So it's just two questions then.
Okay, I'm going to bring Bob back on those in a second, because I think that is also something which is, I think when people hear about the Hyper project, it is very interesting that it does seem to be so much closer than perhaps we generally assume. I think that is something which is worth sort of drawing out, and the fact of those matters. Yes, just one more question first. Keep your hands up, please.
I think people are being... there's a big question that I think people are avoiding, which is, when and how much. Because... I want like lots and lots of limitless, practically limitless power as soon as possible. So we can get on with some really interesting stuff. And this seems to provide, if Bob's right, the potential for something along those lines. So I want to know when we can have it.
Okay. Well, it seems like. Well, I might just let this chap at the front respond, and then if the microphone could be taken back there afterwards, and then I'll bring in Bob. Yes, I know you've got some interaction with the Hyper project as well.
Just a little, yes. I'm very slightly involved with the Hyper project myself. But I wanted to come back on something initially which Alex said, and she was talking about systems which link to more systems tipping points, and then I heard Joe say that actually, or imply, I think, that what's happened with the Gulf Stream so far actually isn't the big bad thing that was hugely overblown in the film The Day After Tomorrow. But the impression I have is that actually we still are very feasibly approaching a tipping point with the Gulf Stream as an example of one of those potentially cataclysmic tipping points which no one really wants to go near, because if that tipping point happens, as I understand it, the whole of northern Europe becomes uninhabitable and unable to feed itself for at least half the year, which has some fairly significant impacts on world society. And just going on from that, my own feeling about fusion, and yes, we are obviously getting closer to it, but it's not something we must overhype as being an instant answer. It takes time. Is that what fusion will do, if used in with all the other technologies, and I include the renewables to a certain extent is it will buy us time to do the things that Alex talks about, the things which are everything to do with managing what we've got better and using that time that we've bought to very much greater advantage. That's what we're really about. And when I briefly talk about the use of fission is very much, and it's got to be part of the future, simply because we won't be ready with fusion fast enough. Fission is capable of the huge energy loads that mankind generates. The maths show that the renewables will make a difference, and we must do everything we can with renewables to increase that difference, but they won't actually make more than a scratch on the surface of the huge energy load that we take on. I just wanted a few comments from that.
Okay, I'm going to bring in other members of the panel in a second. Could you just put that microphone back? And if there's, and I'm just going to let Bob respond, if you wouldn't mind, on the question raised about how close are we really to fusion?
Okay, there was a number of questions raised here, but I'll concentrate on that one, how close we are actually, because it brings in an interesting dimension to the argument actually, which I haven't really mentioned so far. There are experiments going on in America and France at the moment, and within about 2 years, those experiments will have come to fruition. We will actually have demonstrated by then that we will have net energy gain from fusion. That has not been demonstrated before. We do know, however, that those experiments will work. There were experiments done in the 1980s using technology that we're not able to use at the moment in a civilian capacity. But those experiments did demonstrate that you could actually achieve net gain, energy gain from fusion. Now, when I talk about when are we going to get this, that becomes a political decision. At the moment, the price for fusion, if you actually built a fusion reactor, is an unknown quantity. We really don't know how much it would cost. Estimates put it at slightly more than the electrical, say a coal-fired power station, perhaps twice, but not much more than that actually. In fact, it's really a political and an economic decision that would be made whether or not we get fusion in the near term. Now, we believe that if these experiments that we're doing at the Rutherford go ahead, we will be able to shorten the cycle for building a fusion reactor by decades. We will probably have a fusion reactor running by about 2030. Now, that's something like 22 years away. We need to actually do the experiments in the first 10 years, and after that it will take about 10 years or maybe even less to build a fusion reactor. But then again, this is a political decision where we don't know how much money governments throughout the world will throw at this at the moment. They've put 10 billion into ITER. At the moment, our estimated cost for HYPER is roughly about 1 billion euros. That's 10 times less than the ITER program. And ITER will not produce net energy. It will produce energy, but we will not be able to take that energy and power, say, the grid with it. With HYPER, we expect that we'll be able to generate about 500 megawatts. But that, again, will not be directly put into the grid unless things change politically.
Okay, thanks very much. So, close and cheap, it seems. So we're going to have to go quite quickly now. So if people want to speak, please put their hands up and I'll try to get them in. So could you make your contributions quite snappy?
I'm just curious as to what the recent scientific developments have been that allow like a fusion reactor to be that much closer. Because, I mean, you described it being a political barrier that you can't, carry out the experiment to show that you're going to get a net energy gain. But what have been the recent developments that have made it scientifically possible?
Yeah.
Yeah, I mean, the times before our own, when tipping point became popular, was just before the great crash, just after the great crash, and then just after the Cuban Missile Crisis. So I think that a lot of these biological categories, are quite social and political, and they come around at particular times. And I think at the moment, the idea that the nature is essentially stable and harmonious, and then that we act on it, and at some point it sort of flies away on this uncontrollable process. I think it's very much of the moment, and actually bears quite a lot of relationship for example, the vocabulary around terrorism. The idea that you act and there's blowback, complex systems, you can't predict what's going to happen. So I think that it's very much of the times, and what you have now is scientists kind of competing to say that their ecosystem is more fragile than somebody else's. So the North and the South Pole, so the South Pole is kind of trying to say, well, actually, ours is really fragile too. Or people saying, actually, trees are really fragile. And it's almost like the kind of reason to study a species is because it might break down. And that's the kind of question they're asking is at what point does the system break down? And I think that when that becomes a framework for science, it's certainly true that ecological systems are complex. There are points at which they break down. When that becomes the whole framework for your investigation, then it's not surprising that that's the kind of answer you get back more and more. I think the times at which scientists start asking that question is very much less related to the objective reality of nature and more related to the changes in the political conditions.
Thanks for that point. Could we have the microphone down the front, because there's a couple of points here.
My understanding is you can get deuterium from water, I think that's what you said. Can you say a bit more about how you get tritium? I think I saw lithium somewhere, whether you split that into two or whatever. I'm not too sure about the process for getting the other half of it.
Okay, there's a gentleman behind you. Could you pass it back? Can I have the microphone here? Yeah. I'll bring you in a minute, Bob. And
usually with these technologies, people, I suspect, you've tended to ignore the engineering of actually putting electricity in the grid. I also suspect that will take you maybe another 30 years to do, taking account losses as well. Can you expand a bit more on that?
Okay, look, maybe I'll give Bob just a chance to respond to some of these technical points, and then I'm going to take the last question there. Maybe is there one more? Well, I'm going to take the last point here, and then I'm going to bring the panel back to conclude.
Okay, the question about recent developments really is the lasers that are being built just now are much more powerful than have ever been built before, and that's being driven by really the media interest, because they've developed very, very small lasers that everybody uses in their CDs and things like that, and that's the technology that we're using to build the very big lasers, diode pump lasers. We can now compress the lasers to unprecedented short pulses, and that gives us compressed energy, which that we can use to compress the fuel. The other question about, I think, the deuterium tritium cycle, it's actually a deuterium-lithium cycle, because the tritium, although it's produced naturally by cosmic rays in the atmosphere, it doesn't hang around long enough for it to actually remain as a resource on the Earth here. It's got a half-life of about 12 years. What we use is neutrons that come off the fusion cycle to interact with lithium, producing helium and a neutron, and tritium and a neutron actually. So that's how we get the tritium actually, through a lithium interaction with a neutron. Let me say that this has been done, and it's been done for many years, decades. This technology is well known. We know how to do this. It's been perhaps done for about 50 years. And any reactor that's running at the moment, a fission reactor, uses this cycle to produce tritium. So it's a well-known technology.
Thanks for that. So you get a microphone here. Austin, could you pass that? Oh no, sorry. You're gonna. Sorry, I forgot you had. So we got 2 points.
Yeah, just briefly. I mean, it's interesting. It's the end of the conference, because I think some of the themes that have come out have been about risk aversion during the course of the conference, and the fact of fear of the future and a certain miserablism in society and all the rest of it. And then we end up with this kind of quite exciting, futuristic, risk-taking agenda. So I'm just wondering how that fits into the general theme about how we see society. Right? I look back at the 60s and see that as a decade of, jetpacks and goodness knows what, and you know that now they aren't being made. All those kind of technologies, even though the actual science and the materials were there to make it, then they were talked about, and we're certainly not making them now. So how does this project fit into this broader sense of risk aversion?
Thanks for that point.
I'm Canadian, and we're one of the largest uranium exporters in the world, and a lot of our land and rivers are polluted with tailings and the results of that. So my question is, with all the money that is required for fusion, fission, carbon sequestration, couldn't some of that be put into insulating homes, better public transit, improving solar, and making it so that it's not quite as dangerous for lizards, improving wind? I mean, we have these renewables that work, but possibly they're not 21st century, but why not put the money into those things that work and are more or less benign? I just don't understand the mentality? Could someone explain it for me?
Okay, thanks very much. So I'm going to invite the panel to make their closing remarks now. So maybe, Joe, there's been a couple of points directed at you. Are you underestimating tipping points? And maybe you'd like to come back on some of this last question as well.
On the tipping point question, and whether this is something that we really need to concern ourselves with. I think that, as I said before, I think that, too many of these tipping points are actually, rather speculative in the way that they've been put forward. The sense is almost as if we're trying to look for a natural law that can draw a line in the sand that can tell us, the point beyond which we should not go. The sense of the natural limit, as it used to be discussed in terms of a kind of running out resource depletion idea, kind of ran into a bit of trouble because we didn't quite run out in that simplistic way. It seems to me that in many ways, although you can say that complex systems can go into different states and so forth, the discussion about a tipping point is much more this attempt to find some kind of natural limit, a kind of law for society. And I'll just really finish by, going back to the point that I began with, that ambitious energy projects, right? If we have this crisis mentality of we've got to avoid the imminent tipping point, the flipping of the Gulf Stream, whatever else it's going to be, you're going to get the retreat into the bunkers. The idea of what we really need is microgeneration, because then you can kind of feel in control, secure, as we heard this morning, resilient, that you don't have to pay any of the nasty people in the energy company hand over your money. You can go off and live on your own. That's not a viable way forward for an energy supply unless we have confidence that we can negotiate these tipping points. Then we're not going to have fusion.
Thanks very much, Michael. We've only got a couple of minutes now.
Okay, very quickly, 3 points. I think there are. Renewables offer lots of promise, but there is a real issue about how quickly you can roll them out, their scale and reliability, particularly for base load. And they're useful as a supplement. They have a big role to play, but they're not going to cure our energy problems. I don't challenge anything that Alexandra said about complex systems, but and there are obviously exceptions. So it's not a generalisation, but it has been surprising how quickly many ecosystems recover actually from whether it be oil spills or all sorts of things. So it's not, it's not all doom and gloom. So sometimes there are risks we can take. The other is on nuclear fission. I've always been pretty agnostic, but one of the things that I always had nagging away in the back of my mind is a lot of the concern is about dangers to our health and so on. People cite Chernobyl and so on. But the job I had working on coal privatisation was taking over for the taxpayer all the sickness and industrial injury liabilities, a couple of billion, I'm not sure what it is now, it's probably up to 3 billion. Think about the number of people who get killed in forestry, etc., etc. So I think sometimes we get the nuclear fission issue a little out of perspective.
Thanks very much. Alex?
Okay. Well, I'd just like to say, I agree there are a lot of problems with complexity science, but I do think there is a great deal of evidence that these things called tipping points, what have you, actually exist. And it's not only about tipping points, it's about the dynamics of complex natural systems, the economy, society, ecosystems, all these things. And I don't think we should think about this as a sort of way to sort of justify going back to our bunkers. I think we should take it as a great opportunity that we have this science developing, which will allow us to interact with and manage these systems and transition in a creative and innovative way, at responding to the challenges that are presented to us. So complexity science is not just another excuse to go back to the bunkers. It's an opportunity for us to innovate and really interact with these systems with the way they really do work.
Thanks very much, Alex. So, Bob, I'm just going to bring you back in to conclude. I do wonder if, say what finish with what you like, really, but if you would sort of just maybe comment on, do you feel that there is any restraint which is sort of holding back you guys from really, bringing this technology forward in the short term? You sort of hinted that there might be a few, so if you, reflecting on what we said, if you could mention...
Okay, there are a number of issues that we haven't really dealt with here, and one of them is the supply of the fuel. We have to get that sorted. I mean, there is no common supply at the moment. We have to fix that. The containment of the vessel, that's another issue. And the high rep rate lasers. We've got these very high rep rate lasers that exist in CDs and things like that, but we've got to scale that up by factors of billions to get the power that we require. Those are the main issues, but there is nothing that we've seen that will actually hold us back. These are only technological problems. There's no physics problem that we can't, that we've seen that will actually prevent us from doing this.
Great. Okay, well, I think I'm going to bring it to the close then. So I just want to thank all of our panellists.